So now we have this form for the error. It's in the S domain, and this is going to be a lot easier to find the inverse Laplace on. So the inverse Laplace transform, we can see that there's a couple different terms. So we have the time domain and the S domain, and we can see that 1 over S gets transformed between a step function, right? So one of these guys, and then the 1 over S plus A gets transformed into E minus ATs. So we can see that these ones are going to be this bottom one, and this one is going to be transformed into a step function. So when we apply these transforms from the table, right, we can see that this is going to be equal to 1. Its step function goes here. These two, right, get this e to the minus AKT term, right, because this AK is equal to A here. And then they all have the step function on the outside, right, because our Laplace transform should only be valid after time 0. So that's where that step function comes from. So then we're going to combine a couple of these terms because we see we have this these two things that kind of complex coefficients. We're going to combine them together, pull them out, so we have this 1 minus AKT term. All right, great. So now we should notice a couple things, right? All of these, right? This term and this term, when time goes to 0, right? These are going to go down to 0. Or time goes to infinity, these terms are going to go down to 0. So that's going to make these two things go away. So what we're going to be left with then is just this when we approach time equals infinity. So what does this mean? This is what the error, this is what our system error is going to look like after a long time when we assume this very basic transfer function. So we have, this is the amount of error that you would get in our feedback system if the loop the loop filter is equal to 1 in the S domain. And so we could rewrite this using limits. Same thing, say the limit in the time domain is such that as t approaches infinity, we get the difference in the received phase and the VCO phase, right? This is the received, and this is the VCO phase, divided by the input amplitude and some constants related to the VCO. So what are the decay terms in here, though? So we have two decay terms, right? And these decay terms are e to the minus AKT. And we can write decays in a way so that we see a time constant. This is something you may have seen in some basic circuits classes, but we often write these e to the minus whatever as a decay term, where we have a time constant tau. And in this case, when we rearrange this, the time constant tau is 1 over AK. And what you probably remember from your RC circuits, after about 4 to 5 tau, this whole thing has decayed 98% of the way. So if you start at 1, after 4 to 5 tau, right, this is going to be down to less than 0.02, right? It's very low. So this is, after 4 or 5 tau, we're going to have a very small error, but it's going to be a constant error of this form. So what we've seen is with this basic analysis, where we had that loop filter, where h of s is equal to 1, we got this equation for the error in the time domain. And the error in the time domain, it starts out at something, but it decays fairly rapidly with some time constant based on your system parameters. That's going to give you this in the limit. This is going to be your limit to the error in time. So coming out from the VCO, you have a output phase, and after 4 to 5 over AK, so after 4 to 5 time constants, this is what your phase error is going to become. And we remember that the input phase was given as this, right? This was the input phase that we rewrote when our input had some omega naught that was not equal to the VCO free running frequency, and also some phase a difference as well. So based on the definition of phase error that we now see, right, we have error in time domain. We also know what the input is, so we can find what the output is. So we can rearrange this, get the output phase error, and the output phase, just the output phase, the output phase is equal to this, where this comes from the input, and this comes from the error term. And if we now put this in, right, we have the output phase from the VCO that was rewritten in terms of the input phase and the phase error that we found through inverse Laplace transforms. We can substitute that output phase into here. And then after 4 or 5 tau, we can now say that our VCO produces a oscillating signal that looks like this. And we remember that our received input signal, right, was omega 0 and phi 0. And so we can see that our output VCO was able to get very close here and here, and it just has this amount of error that was remaining. So we received some input signal that had a different frequency than the free running frequency of the VCO and some phase offset. And then based on that, we used our knowledge, used feedback analysis. We used the definition of here in the S domain. And we were able to figure out what the time domain error was going to be, and we can see that this is what the phase difference is going to look like. So this is nearly identical, right, except for this small amount of phase error. Plus, recall, right, there is also that constant pi half phase difference that's due to the fact that the VCO was essentially an integrator.